Right, we'll start today's lecture. Yesterday we discussed about all the basic properties of crystalline materials, and also we looked into the differences between crystalline and amorphous materials, right? So, you can easily recognize a crystalline material if it is well orderly arranged. Okay, so orderly arrangement means not only in a short range but also in long range also, right? So for example, you can see some kind of pattern, right? Let's take the pattern along this direction, right? So you have this unit, this particular unit is repeating, right? It's going here and also it's there like this, right? So in the same way you can find this unit repeating this way, right? If you continued it, you will see the same order, or otherwise you can take this unit and you can see it's repeating, right? So this type of short term and long term, right? Short order or long order. Short order means just immediately in the vicinity of the points. Okay, so here or here you will see some orderly arrangement, right? The same unit repeating, right? At the same time, if you can see in the long term, right? For example, if you have some I mean continuous structure up to here, right? You may see the same unit is repeating, so that you can define it as a crystalline material, right? So another thing is the amorphous material that you can see, uh, they don't have uh, kind of repetition. Probably they may have repetition in short range, right? For example, here you may see some short range repetition, right? But in the long run you don't see that, right? Maybe very short length you may have repetitive units, but still they are not orderly arranged, right? You can see they are in different directions. This unit is in this direction and this unit is here, right? So in the immediate vicinity you don't see very well orderly arranged, although you might see some short range orders in some areas of the material, not every place, right? Only in some areas. So that means it's definitely heterogeneously distributed. The ordering is not heterogeneous. I mean, is not homogeneously distributed. It's distributed heterogeneously. Okay. So anyway, without any orderly arrangement, without without repetitive orderly arrangement of units, any material you can call amorphous, right? You can call these amorphous materials, right? So short range might be there, but mostly you don't see that also, right? Long range, it's not anyway, right? So this is the difference between crystalline and amorphous materials. Okay, and now let's see physical differences between the solids, gases, and liquids, right? So you know already all these details, but in terms of crystallography, it's important that you remind them, right? So the first column shows the representation of the state. That means whether it is gas, liquid, or crystal, right? Then the second one says the retention of shape. Retention of shape is shown here in the second column. That means whether the shape can be preserved or not, right? And the third column, retention of volume, whether the volume can be preserved or not under different conditions, right? And then the distribution of molecules is shown here, and the physical properties are also shown here, whether these materials are isotropic or anisotropic, right? So we are looking at whether the materials are isotropic or or anisotropic, right? So you can take the gas here. So you see the gas molecules randomly distributed, right? They are randomly distributed, but the same gas molecule, for example, if it is oxygen, O2 should be there, right? If it is hydrogen, H2 should be there. So they are distributed in a given area where they are present, and the shape. Is there any shape for gaseous objects? In the atmosphere you can find gases, right? So you can put some atmospheric gases into a bottle and put it in there, and also you can put them in a box also, right? If you put it in a sealed box, you will still see the gas remained in the box, right? So what about the shape? If there was a shape, uh, like for example, if you had some kind of a bottle shape gas, for example, right? You think that a gas, in one place you can find a gaseous object which has a shape of a bottle, right? So can you put that in a box? I mean, if the box is small, you can't put it there, right? If you have a big box, then of course you can put it. But uh, I'm asking whether there is any shape for the gaseous objects, right? There is no shape, right? That's, it takes the shape of probably it takes the shape of the container, right? That is in that is contained in, right? But still there is, I think it's not, there is no shape at all, right? What about the volume? Can you think the volume is constant uh, for a given gas? What about you take some gas and put in different sized containers, right? Is it constant? Okay, you can think like this. Maybe you take a piston and cylinder. Oh, sorry, piston. Yeah, piston, piston and cylinder apparatus, or what? Simply bicycle pump. Bicycle pump you can take, and you try to push it. Right, there is some volume there. Right, there is some volume of air there, but you can still push it. Right, you can push it and reduce the volume. That's possible, right? So that means the same mass of volume, you try to change the pressure, change the volume, the same mass of gas, you try to change the volume, right? You were able to change the volume, right? So that means there is no constancy, right? There is no retention of shape or retention of uh, what the volume, okay? Right. So don't forget to put your numbers, registration numbers in the chat box also. And if you take a liquid, what's the situation, right? You can put some liquids in different containers and see whether they have the shape, retention of shape. Usually what happens for the liquids? It takes normally the shape of the container, isn't it? Right? If you put some water into differently shaped bottles, still the water will have different, I mean, that volume will show you in different shapes according to the shape of the bottle, right? So that means there is no shape also. What about the volume? Yes, there is some retention of volume, right? There is retention of volume. That's why you often see uh, overflowing, right? Overflowing tanks, right? There is a limit of volume, right? So retention of volume is there for liquids. And if you see the solids, what happens for the solids? Solid, they have shape. Yes, they have shape, and also they have retention. They can show the retention of volume property as well. Okay, So retention of shape and retention of volume both is available for a solid. So do the crystals. Crystals also same, right? Because they are solids. So this property is important for us when studying these mineralogical and crystallographical properties of materials, right? And regarding the third column item, distribution of molecules, right? So random in gas, right? Probably in the volume, in the gas and liquid, maybe some homogeneity is there, right? There can be some homogeneity. That's why you can measure the composition of the atmosphere in different places, right? You will get the same composition, right? So 78 of percentage of nitrogen is there, right? It doesn't change from Japan or from US or Sri Lanka, right? When you measure, it's almost, I mean, there is no change, right? So statistically homogeneous, you can say that statistically homogeneous, right? For the volume or for the liquid also same. The molecules are homogeneously distributed within the liquid for a given liquid, right? There can be some heterogeneous liquids, but in general, we are talking about, okay? Right, and crystal, what do you think for solids? Not all solids are homogeneous in distribution of molecules, right? So that's why we have crystalline materials and non-crystalline materials, right? In crystalline materials, the molecules are distributed in a orderly manner. That means in some way of homogeneous behavior, right? So this is what we call the periodic homogeneity, right? Periodically homogeneous. They are periodically homogeneous means they have some repeating units. For example, as you saw here, they are homogeneous but periodically, right? From this point to this point, it's not homogeneous because they have two shapes and two sizes, two volumes. But if you take this as a unit and it is repeating here again and again, so that means it's periodically homogeneous. So crystals are periodically homogeneous in terms of distribution of molecules. So physical properties, considering these facts, we can say that gases and liquids are in general isotropic. In general, isotropic. That means their properties are same in all directions. Their properties are same or similar, more or less similar. I mean, closely equal in all directions. Okay. So this is what we call isotropic nature of matter. Isotropic nature of matter. Properties are equal in all directions, especially the physical properties. Okay, physical properties. But of course, different physical properties may have different behaviors in different directions. That is obvious, right? For example, the electricity and conductivity or something, right? They may have different behaviors in different directions, but in one direction, a given property should show homogeneous distribution. Okay, so in a crystal, there are some directions where you can expect isotropic behavior, right? But remember, it's not in all directions. It's not in all directions. You can't expect isotropic behavior for physical properties, right? But for some physical properties, like for example, some optical properties of crystals, for example, right? For garnet-like minerals or crystals, they are equal in all directions. So actually, both isotropic and anisotropic behavior can be expected in crystals, right? So it's better to write here anisotropic or isotropic, because in certain directions it's anisotropic, but in certain directions it may be isotropic, right? You can remember the piezoelectricity and pyroelectricity. They are dependent on different directions, right? For example, in one crystal, maybe it's elongated direction, everything is isotropic, but in the opposite direction, perpendicular direction, it's not isotropic, right? So like that, there can be differences in crystals. Okay, so these are some properties of matter. So that applies for crystals as well, right? Because crystals are solid. Okay, right. So this homogeneity again, if we show that in a diagram, right? You can see some different types of homogeneity, right? We already discussed about this homogeneity, uh, whether they are periodic or statistical, right? Statistical means there is no orderly distribution, right? But in terms of counting the molecules, in terms of numbers, you count them, then you can find some homogeneity. That means concentration wise, it may be homogeneous. Counting means concentration, right? You determine how many molecules are there of oxygen, for example, out of the entire mass of 10,000 particles, right? That is ppm, parts per million, or weight percentages. In 100, if you consider 100 molecules, how many are there uh, in your interested molecule? How many are there, right? So that is a weight percentage. So likewise, it's a statistical homogeneity, but in some other materials, it can be periodic homogeneity, right? So in this case, the statistical homogeneity in this diagram, according to this diagram, you can see the same behavior in parallel directions, same behavior in parallel direction, so that you can have isotropic behavior. You can have isotropic behavior because you have the same behavior in parallel directions. Okay, right. So if you consider the periodic homogeneity, uh, it's different directions, you may see different behaviors. For example, we took one example here, right? Along this direction, we saw that this particular unit is repeating, right? So in that direction, it is homogeneous. But to the other direction, it's not like that, right? For the other direction, you have this unit, but the next place like this, and again, you should have that. In that case, it should be homogeneous, periodically homogeneous. But if you take the second row, the periodicity is different. It's periodic with a different configuration, right? The big one is occurring in the second place, not in the first place, like in the previous case. So if you see the first line, third line, and fifth line, first line, third line, and fifth line, what do you see? Same orderly arrangement, same orderly arrangement. Okay, so that is what you call the periodic homogeneity. So every other line you have the same composition, right? So every other line means one after the other. So that's it's periodic, right? One after the other, not one. I mean, sorry, not one after the other. Every other occasion, right? Every other occasion, right? So first occasion, two, no. Third, yes. Four, no. Fifth, like that, right? So that is periodic homogeneity. So you can have a periodic homogeneity in uh, in crystals, there you can clearly see which as an anisotropic property. It should be an anisotropic property because uh, in parallel directions you don't see the same type of distribution. Okay, right. Always remember these crystals have periodic homogeneity, and this periodic homogeneity is caused by the unit cell, right? Remember the unit cell we discussed last time, the smallest repeating unit, right? There can be several repeating units, but the smallest one is the unit cell. So you can see the unit cell is changing in different directions, right? So here also you can see the unit cell, right? You can see here the unit cell in this way, right? So one repetitive unit and another repetitive unit is here, right? So like that you can find a single repetitive unit which can be the smallest representing the entire crystalline material, right? Representing the entire crystalline material. Okay, right. So let me check your chat box. You are not giving me any time. You can't say yet. Okay, please think over a time slot and contact Dr. Nadisha, right? Please contact Dr. Nadisha also for that. Right. Uh, Sorry, I think I have muted, right? You didn't hear anything. Okay, anyway, so I was discussing about the nature of graphite, uh, nature of graphite, or the bonding nature of graphite, right? So here you can see they are related to each other like layers, right? You can see the layers. You can see the layers here, one by one, right? So in between, what do you have? There is nothing in between. So weakly bonded layers are there. So weak van der Waals forces are there. So that's why we find some kind of slippery nature, in graphite. So these each layers are moving or slipping relative to each other, right? Because of this weak bonding in between. Okay. So that's why this nature or this physical property is used effectively in lubrication, producing lubrication materials, right? So as a lubricant, graphite is good because of this slippery nature due to this arrangement, right? You can see orderly arrangement of graphite unit cell here, right? This one and this one like this, right? So these are the unit cells. So it's showing the crystalline nature of graphite like this. So their properties are different. Electrical conductivity, for example, in this direction is different from the opposite direction, right? So that is the nature of graphite uh, that you can find in the in Sri Lanka. You see very good quality graphite is found, right? We don't have any impurities in our graphite. That's why we have high quality carbon percentage above 99.95, right? That's a very good grade. That's why Sri Lankan graphite is very pure. Sri Lankan graphite is crystallized by a fluid about at least 600 million years ago in the Earth's interior. Uh, we call that time is the pre-Gondwana time, right? Uh, Due to some fluid activity internally within the Earth's interior, this graphite crystallization has taken place. Okay, so actually some graphite can be formed by subduction also or burial also when organic materials which are rich in carbon buried like producing peat. See, you can remember the peat, production of peat, that's shallow. Peat is produced, that is also carbon from the buried wood, right? But if this wood were allowed to bury very deep, like some 30-40 kilometers, they will convert into uh, crystalline carbon. Okay, they will convert into crystalline carbon. First, they will convert into peat and then graphite. Right, graphite is crystalline carbon. And after that, what happens? If further burial is there, this graphite can be converted into another form of carbon, which prefers high pressure conditions. What is that? Yes, can anybody tell me? What is the high pressure form of graphite or form of carbon? High pressure variety, high pressure form of carbon. Moderate pressure form is graphite. Okay, what's the high pressure form? Yes, diamond. Yeah, that's correct. Diamond. So graphite can be converted into diamond if you pressurize it further and further, right? In experiments or in laboratories, we can produce diamond from even organic material, cellulose, right? There are some experiments we call experimental petrology. So people doing experimental petrology, they synthesize minerals in the lab, they synthesize different minerals in the lab, right? Some minerals you can find only in the deep mantle, right? Deep mantle means some more than 1,000 kilometers below the surface. Some even you can't find them in rocks because that deep part of the mantle cannot be taken up to the shallow levels of the earth because there is no volcanism or anything in that area, right? 1,000 kilometers is very deep. Volcanism and all seafloor magmatism, everything is very shallow, right? Up to like 100 kilometers. Beyond that, there are no magmatic flow coming up. Only very rare occasion is there. That's once in like 400 million years. Once in 400 million years, like, right? That's we call mantle plume. Mantle plume. You can search what a mantle plume is, and also you will learn about that thing in your third year. So mantle plume is a magma, a special type of a magma, which is very very hot, which is much hotter than the normal volcanic magmas, right? You know how hot the volcanoes, right? How hot the volcanic magma. But if you think 3 4 times hotter than those magmas, can you imagine how much temperature would be there, right? Maybe 400 Celsius, 500, like that. That magma is coming one as a batch, as a big batch, once in 400 million years. So that causes, actually it's coming up not slowly, very rapidly, and it has huge, uh, huge pressure and temperature. So it can hit the shallow crust. It can hit the shallow crust and disperse into pieces, right? So the world's end is there, right? Every 400 million years time, all these continents in the world, oceans, continents, everything is get destroyed by these plume hits, right? uh, one time about 200 million years ago, such plume hit, and now you can see the Hawaiian Islands are formed after a plume hit, right? Hawaiian Islands are the crystallized products of that type of magma, that type of hot magma, special magma of plume magma, right? So about 500 million years ago also, right? 600 million years ago, like approximately, another plume was hitting that uh, not actually, yeah, around 650 700, like there uh, the the then existing continents and oceans were everything destroyed, right? That was at that time we call it was a super continent, right? uh, Called Rodinia supercontinent, that was destroyed and uh, into pieces. After that, sometime later, maybe another 200 million years later, a new continent, new supercontinent, a very big continent. Supercontinents means very large continents, right? You know how large a continent is, right? Africa, Russia, Eurasia, like continents, America, you know, they are how large they are, right? Compared to our country. But supercontinents means collection of such large continents. So it should be very, very huge, right? More than 90% of all the continental mass is concentrated within a one continent. That is a supercontinent. And these supercontinents even get destroyed by these mantle plumes, right? So this type of things are there, very interesting things are there in geology. So I think you can learn about those things in the near future. Okay. Right. So coming back, we have these crystal structures, right? Graphite is one of the crystal structure that you can find with having anisotropic behavior in terms of conductivity, right? So we discussed about uh, some other minerals yesterday, right? For example, diamond and quartz, right? Diamond is the the high pressure variety as we just talked, but it has similar crystallographic orientations, right? We discussed this, but quartz, it has a different crystallographic orientation because these axes are different. So anisotropy is there in quartz very easily. Isotropy is there in diamond, right? So for example, if you take simple optical features, if you observe diamond and quartz under microscope, right, optically you will see similar features, even though you rotate your object, your graphite or your diamond crystal. If you rotate, but still you see the same colors, same ways of changing patterns, or I mean, some colors are changing while you rotate the material, because these interfacial angles make the light rays to be refracted in different directions, right? They are not in equal directions, but the color and everything caused by those refraction and all are equal in all the directions. That therefore you can see the same optical properties of diamond in all directions equally. But quartz, they have different the crystallographic orientations of this distribution of crystallographic axes, etc., that make these properties changing in different directions. So it's anisotropic, right? So we saw another one, but yeah, this type of things, right? Piezoelectricity or pyroelectricity, they may be also different, right, in certain directions. So they are anisotropic, right? So this effect is anisotropic. So conductivity also behaves like that, right? In one direction it's different, and the other direction the variation is the behavior of its change is different, right? So this is an important feature of minerals, right? So you have to keep in mind that these physical properties can be variable depending on their internal structure, right? Internal crystal structure. Okay, so do you have any questions? Any questions? Right. So please let us know about free slot, because tomorrow's lecture Dr. Nadisha cannot take from 8 to 9. So she has to do one lecture anyway. You must have a lecture, because otherwise when the universities are open, there is no time for, I mean, there may be no slots enough for catching up the extra hours, right? Because every subject in the faculty will be looking for extra slots, right? So and practicals are coming, so you will be you will be, I mean, get burdened with a lot of workload in that case, right? Therefore it's better to finish as much as possible early, so that you can get some kind of a relief, right? So better to finish it's not just 1 hour, maybe 2 hours is also okay in this week, so that she can cover the last week's part also. Okay, right. So I don't know whether she started last week the section, but anyway, she cannot do it this week and onwards. So therefore, you have to definitely change the slot, change the time, right? So let's see. I'm also not available, so otherwise I could have taken it and exchanged it. But I'm also not available. So please contact her. Okay, so I want to stop here for today. So we'll meet next week.